what I'm going to talk about, I'll illustrate in examples to do with implicit learning, but the issue is entirely general, and what I have to say will apply to any data that you analyze whatsoever. So in the case of implicit learning research, how would you establish that you're dealing with a distinctively implicit situation? Well, you might say there's unconscious knowledge involved because there's no conscious knowledge as determined by getting a non-significant result on a test of conscious knowledge. At least that would be one way of proceeding here. Now, the problem with this is the interpretation of a non-significant result. What does it mean? And as you probably know, a non-significant result could mean two things. It could mean that you have good evidence for no difference, good evidence for the null hypothesis, or it might mean that you have no evidence for anything at all. The evidence just doesn't count for much one way or the other. And as you appreciate, this is entirely a general problem in terms of the workshop that we just had. Let's say you concluded that there was no N400 in a certain condition. Well, if you did that just on the basis of a non-significant result, there'll be a problem. And one way of thinking about that problem is this. When we analyze data, we divide the world up into two states. One of them we call H0, the null hypothesis. Let's say that's no difference, no effect, no correlation. And then there's an alternative hypothesis, we'll call it H1, saying there is an effect, there is a difference, something like that. Now, in general, we can think of what our data as providing us with is either good evidence for H0, good evidence for H1, or no evidence to speak of. Would like to know which one it is, right? Now, p-values make a two-way distinction. So they distinguish the things in that right-hand box, evidence for H0 and no evidence to speak of. Those things are lumped together and contrasted with evidence for H1. I mean, in fact, arguably, p-values aren't a good measure of evidence in any way, but actually, I mean, as a community of psychologists, statistical users, we're not completely stupid. There are conditions under which p-values do express some evidence, and when they do that, they're distinguishing those two states of affairs. And in particular, no matter what the p-value, no distinction is made within that box there. So one thing you can't say is my p-value is really high, my p-value is 0.9, so there really wasn't a difference. Okay. Well, maybe your p-value was 0.9 because you had a big standard error. Right? It's just your data were insensitive and not diagnostic of anything at all. Another way of thinking about this, I think, is usefully shown by some software the Australian psychologist Jeff Cummins has on his website. This is some Excel software. I don't know if you've seen it. He calls it the dance of the p-values. It's just a little Excel macro. I ran it and took a screenshot, and this is what I got. So here what we have is a p-value. These are p-values. And this is a simulated experiment where there really is an effect. And it's a repeated running of the same experiment. Because it's a simulation, we know everything is the same in successive runs of the experiment, except for the vagaries of random noise, of random sampling. So of course results differ, not because the population effect has changed, not because you're dealing with a different group of subjects, not because it's sunny rather than rainy, just because you're dealing with randomness and sometimes results go a bit more one way rather than another way. So on the first run of the experiment that I happened to catch on the screen, there was a p-value of 0.23. Okay. And then on the next run it was 0.144. So you see you get a mixture of significant and non-significant results. Now one of the first things to notice is just how wildly different p-values can be when you're dealing with essentially exactly the same situation. Up here there's a p-value of 0.028, and if you got that, you'd be extremely happy. You'd say your experiment worked. But then if you replicated exactly the same experiment and you got a p of 0.817, which happens to be the next run of this program, you would say, my God, what went wrong? Who was that RA I employed? And you'd think there was something that needed to be explained, right? And probably, I mean, if you went through this as successive runs of your experiment, you would have manic depression. But the main thing I want you to take home from this is we're dealing with exactly the same situation here, and this is how wildly variable p-values can be when there really is an effect there, and we're trying to pick it up under normal conditions of 50% power. So a p-value of, say, 0.8, 0.47, 0.6, this really doesn't mean that there is no effect or that you have good evidence for no effect, right? That can easily arise when there really is an effect. So how can we solve the problem? Well, I mentioned that p-values aren't really good measures of evidence. So let's say we start from first principles and try to come up with a measure of evidence. And that leads us to the Bayes factor and to Zoltan's box of mystery, also known as Zoltan's box of pain, because the question is, what is inside the box? There's two possibilities: Tasmanian devil or cat. I don't know if you know the Tasmanian devil. Looks very cute, but its brain size is about that big and has one of the strongest bite strengths on the land animal kingdom. So if you go down and pet the little fella, he takes a bite. He could go through your finger, basically like it was butter, just and slice it off. So if you ever go bushwalking in Tasmania, which I have done, and you see the white poo on the ground, that's devil's poo. And that's because when it eats carcasses, it eats through all the bone, and then it comes out in the poo. So if the devil's in the box, and you put your hand in the box, there's a good chance when you take it out, you'll only have 4 fingers left. Now, I don't know if you know that cat over there. Again, it looks cute. He's a pretty nice cat, actually. But if you do know him, you know he does have a vicious side just sometimes, right? He's from Shrek. So you might lose your finger if the cat is in the box, but it's less likely. In fact, at the University of Sussex, I've tested this box extensively on undergraduates, and I can give you some precise probabilities. If the devil's in the box, you'll lose your finger 9/10 of the time. And if the cat's in the box, it's only 1/10. So now here's the principle, which I hope strikes you intuitive. You can sort of derive it from first principles if you thought about what do we want from measure of evidence, and you sort of, go through some mathematics and so on, a bit of philosophy. You can come up with something like this. But the basic idea just hope strikes you as sensible, that evidence supports the theory that most strongly predicted it. Right. So if a theory says precisely this must happen, and it happens, that's pretty good evidence. And if a theory says it can't happen, and it does happen, well, then the theory must be wrong. So let's say I put my box on the table. Actually, I had John there. I didn't realize John Williams. Wasn't thinking John Williams would be here. But let's just say it's John. Randomly selected. John puts his hand in the box. He takes it out. There's only 4 fingers there. So which hypothesis is most strongly supported? The cat hypothesis or the devil hypothesis? So just bearing in mind, evidence supports the theory that most strongly predicted it. So that particular outcome is predicted with a probability of 0.9 with the devil hypothesis, 0.1 with the cat. So it supports the devil hypothesis more, right? And let's say we wanted to express how strong is the evidence. Well, why don't we just divide that 9/10 by the 1/10 to get a measure of strength of evidence. So if you can't read the bottom there, it says the strength of the evidence for the devil over the cat hypothesis is 9/10 divided by 1/10, which is 9. And in fact, that is the Bayes factor in this situation for the devil rather than the cat hypothesis. You say the evidence is 9 times as strong for the devil over the cat hypothesis. Or consider, let's say that didn't happen. I put the box on the table. John puts his hand in it, takes it out, all the fingers are intact. So now which hypothesis is most strongly supported? Well, I'd set it up so it's symmetrical. This is predicted 9/10 of the time by the cat hypothesis, 1/10 of the time by the devil. So now the Bayes factor is 9 for the cat over the devil hypothesis. Or you can say it's 1/9 for the devil rather than the cat. It doesn't matter which way around you put it. Okay, different situation. I get a different cat and a different Tasmanian devil, slightly different personalities than the ones I had before. So I extensively test on the undergraduates again. And this time the probabilities, there's still a difference. Probability of losing a finger given the cat is 4/10, and probability of losing the finger given the devil is 6/10. So now what they predict isn't quite so different, right? So now if John loses a finger when he puts his hand in, and I said to you, what do you think is in there, a devil or a cat? And let's say I was 50-50 beforehand. You'll probably say, well, it could be either really. The evidence isn't really that strong. Okay. And if we express the strength of the evidence in the same way, it's dividing the one probability by the other would get 1.5, the Bayes factor is 1.5, and I hope you have the intuition in this situation that I wouldn't really know what's in there, a devil or a cat. The evidence just isn't particularly compelling one way or the other. Does that make sense? Any questions? So now I've given you 3 states of affairs. In one case, we had strong evidence for one hypothesis rather than the other, or strong evidence the other way around, or not much evidence either way. So we've already made a 3-way distinction that we couldn't make with p-values. And one way of saying that is that principle up there, evidence supports the theory that most strongly predicted it. P-values don't respect that principle. So if you think that principle makes sense, then p-values isn't the way to proceed. And indeed, the Bayes factor we can apply to sort of more complex situations, like, for example, where you do a t-test or correlation. In fact, anything, any inferential statistic you do at all, to give a measure of strength for one hypothesis rather than another. And the way that I've programmed my online calculator, it's the strength of evidence for the alternative hypothesis relative to the null. Okay. So now a Bayes factor of 1 means the data are just as strongly predicted, are equally well predicted by H0 and the alternative. So therefore the data are in no way discriminating between the 2 theories. And if the Bayes factor is more than 1, well, the more it departs from 1, the bigger it is, then the more strongly it supports H1 rather than H0. And the more it's below 1 and towards 0, the more strongly it supports H0. So a Bayes factor of about 1 means experiment was not sensitive, you need more data. And you might say, well, how close to 1 does it need to be, or how far away from 1 should it be before we say we have strong evidence? Well, that's really just a matter of convention. I mean, intrinsically, Bayes gives you a continuous strength of evidence. So some Bayesians say, I don't like to put cutoffs there, but I think cutoffs are fairly useful, as long as you remember their conventions. And unlike with hypothesis testing in orthodoxy, there is no black and white jump. 0.05 in orthodox hypothesis testing marks a black and white boundary. That does not exist in Bayes. There's just some conventional cutoffs we can put there to help us interpret what it might mean. Well, Bayes factors were in fact first developed by Jeffreys, who is a Cambridge physicist, geophysicist, astrophysicist. And he suggested a convention of 3 or more as being substantial evidence, and by symmetry, a third or less being substantial evidence, and in between being evidence that's barely worth a mention. Incidentally, something we now know that we didn't know until extremely recently because of declassifying files, Alan Turing also developed Bayes factors, possibly independently, although they were both at Cambridge, in order to decode German codes, in order to say, well, what might this particular code be standing for? Well, we can have a measure of strength of evidence. It could be this, this, or this, and watch the evidence build up as you collect more data until you have good evidence for one particular thing. And that helped him bust German codes during the war. Now, I think that Jeffreys chose 3, cutoff as 3 or a third, not arbitrarily, but for good reason. Now, he was around Cambridge, same time as Fisher. In fact, they lived 1 minute's walk away from each other. And Fisher came up with the 5% significance level that we've adopted. And in fact, Jeffreys said he regarded his methods as mostly producing the same answers as Fisher's. And what I found in analyzing hundreds of data sets in psychology, that when you get a significant result, just significant at the 5% level, and the mean you obtained would be roughly that you would expect, that a 5% significance level corresponds to a Bayes factor of roughly 3 or more. So in other words, Bayes factor of 3 was well chosen in reflecting the sort of evidence that we as a community of scientists have been used to taking as just good enough to start doing something with. So if 3 is non-arbitrary in the sense of reflecting general scientific practice in a rough sense, then by symmetry, a third or less will be the criterion for good evidence for the null hypothesis to exactly the same amount. Now, incidentally, just so there's no confusion, there is no necessary relationship at all between a Bayes factor and a p-value. So when I say often I find 5% significance goes with a Bayes factor of 3, that's just often as it happens. Practically, that's what I found. That is not a mathematical relationship. In fact, you can prove mathematically quite the opposite, and you can indeed find the opposite, that a significant result might even be, on a Bayesian account, support for the null hypothesis. And situation where you're likely to find that is if you ran until you got a significant result. So you ended up running a lot of subjects to get a just significant result. A Bayesian analysis might well tell you you have good evidence for the null hypothesis under those conditions. So a Bayes factor makes the required 3-way distinction that the p-value didn't. If you have a Bayes factor between 0 and a third, you can say, we've got substantial evidence for H0. And if it's more than 3, we'll say we've got substantial evidence for H1. And if it's in between a third and 3, it's insensitive. In fact, one thing you're allowed to do with Bayesian statistics you're not allowed to do with orthodoxy is you could simply collect more data. You say, I don't have enough data now because it's insensitive. I'll run another 10 subjects and check again. And in fact, you could keep running and checking until the Bayes factor was more than 3 or less than a third, and you knew that you had sensitive data. You're strictly forbidden from doing that in the orthodox framework if you're using significance testing. So one corollary of that, by the way, is if you have run an experiment and you get p equals 0.08, you're not allowed to run 10 more subjects, right? And then see if it's significant. In fact, there's really nothing you can do from an orthodox point of view at that point. What you have to do is become Bayesian, collect more data, and do a Bayesian analysis because you're allowed to do that. Now, the principle which the Bayes factor is based on, which I illustrated with the cat and the devil, is theory. Evidence supports the theory that most strongly predicted it. So what that means is, in order to test our theories, we need to know what they predict. I hope that sounds sensible to you. So now, with the null hypothesis, we know what it predicts, and I'm just illustrating there one way of representing what it predicts. On the y-axis is the plausibility of different population values, and at the bottom there is different possible population mean differences between conditions. Now, what the null hypothesis says is there's only one plausible, indeed only one possible population difference, and that's 0. I mean, it could be something else, but let's just say 0. The null hypothesis is saying the population difference is 0, and that's that. Okay? So we can represent that as a spike there at 0, okay? Saying that's the plausible value. But now this is the next bit is the difficult bit, and this is where if you're going to criticize Bayes, where you would criticize it, and this is where when you go over to doing Bayes, you need to think a bit differently than you used to. You need to say, what does your theory predict? So you need to say, well, I expect a difference here, but is there a maximum value to that difference? Is there a most plausible value? Is there a minimum value? What's the range of possible differences consistent with my theory? Are there some differences ruled out by my theory? So now that so when I first looked into Bayes and I wrote my book on understanding psychology of a science, at that point I hadn't thought about exactly are there any principles by which one thinks about this in order to really do Bayesian analysis with one's data. And so for a couple of years I set my graduate students, or all the graduate students in psychology at Sussex, which is about 100 in a year, on a methodology course, they'd choose a paper and do a Bayesian analysis on it. So then in the space of a year, I thought about 100 different papers and how would you do a Bayesian analysis on it. And I realized actually there's some simple rules of thumb that cover almost all cases. And now I'm in the situation where I realize this isn't a difficult problem. I know it'll seem difficult at first, but once you've been through examples, it's not that difficult. Some rules of thumb, which if you told me your experiment, I could probably, in a matter of 30 seconds, as long as I've understood what your experiment is, tell you how to approach this. And the other thing I'll say is even if you didn't become Bayesian, we were meant to be thinking about this anyway. So to do hypothesis testing properly, we're meant to be doing power calculations. Okay? And that means specifying an effect size. Or we're meant to be thinking in terms of confidence intervals. But actually, to fully interpret confidence intervals, you need to know a minimal plausible effect size if you want to be able to assert a null hypothesis. So we're meant to be doing this anyway. It's just we didn't have to get out a p-value. And so we've been escaping an aspect of analysis that is logically necessary to think about if you want to if you ever want to get support for a null hypothesis. And we just escaped it because we could. So what I'm hoping is a Bayesian analysis, at least the way I do Bayes, forces you to think about everything that's inferentially relevant to drawing conclusions. So what I'm going to go through is some ways of thinking about this, and the way I've programmed it up is if you're thinking about the plot of the plausibility of different effect sizes, population differences between your means or population correlation values, that plot could be uniform, normal, or half normal. And it sounds a bit odd to you. Now, let me just go through what I mean by this, and we'll have done the difficult bit. So let's imagine we're running an experiment, and we're interested in whether imagining a sport move, like swinging a golf club, for 10 minutes every day for a week will improve our sporting performance. And so what we do is we get people to imagine swinging a golf club and hitting a ball for 10 minutes a day for a week, and we measure the number of balls in the hole before and afterwards, and we get a non-significant result. Maybe we have a control group where they imagine something else. Okay. So we get a non-significant result. What does that mean? Well, the key take-home message I want you to take away from this talk, if you take away nothing else, is it means nothing at all. Okay? When you get a non-significant result, and a non-significant result by itself means nothing at all. No conclusion follows whatsoever, just from knowing that a result is non-significant. What we need is to have a handle on the sort of effect size that we wanted to pick up. Right? I mean, you say, I might have a confidence interval like that. Is that a small confidence interval? Is that a large confidence interval? Well, I don't know until I know the difference I wanted to pick up, right? So how would we get a handle on that? Well, I think what I would do in this situation is I'd get people to actually swing a golf club for 10 minutes a day for a week and see how much that improves performance on my measure. Now, my guess is that actually swinging a golf club, actually doing a sports movement, would set an upper limit on the effect that imagination could produce. Maybe imagination is as good as that, but I doubt that it's better than that. Okay? I think doing it, I don't work in this area, but I'm just guessing that doing something for real is better practice than doing it in your imagination. So let's say we run truckloads of subjects to get a really good estimate of the effect of really swinging a golf club. And let's say they get 8 more balls in the hole afterwards from a week of practice. So this is a situation where I'd use a uniform distribution. You could say, I don't know what imagination does, but it's going to improve your performance by somewhere between 0 and 8. Okay, might improve your performance by 1 ball, 2, okay, up to 0 to 8. Now, what the uniform is saying is all the values between 0 and 8 are equally likely. And if you're willing to say that and put 8 as the maximum, then that's the representation of the alternative hypothesis. And in fact, that's typically what I do when I can think of a way of specifying a reasonable maximum to what I could expect. I put a uniform from 0 to that maximum. Now, another sort of situation is you don't think of a maximum, but you think of, a roughly expected sort of value. Using this paradigm, similar sorts of manipulations. Let's say the dependent variable is a percentage scale. Similar sort of manipulations have changed performance by 5%. So it's not a maximum, it's just the sort of effect I might expect. So it's the sort of thing people typically put into power calculations. Okay. What sort of effect do you expect here? Well, ideally you might do a meta-analysis, or you base it on another experiment that's similar to yours, and or possibly you base it on a pilot experiment and you say this is the sort of effect that I'm expecting to get. So then what you could do is represent your theory with a normal peaking at 5%. So you say 5% is just an estimate. I really don't know if it's exactly 5%. Could be 4%, could be 7%, who knows. So we spread it out with a normal distribution. Just to go back to the uniform, I just want to mention something. Notice here this uniform all goes in the positive direction, because what it's saying here is imagining the move is going to improve me. It's not going to make me worse. Negative numbers here just means your means go in the other direction, and that would mean that we're doing worse than the control condition. So this theory specifies a direction. If it didn't specify a direction, you could have extended the uniform out either side. But here there's a clear direction. We're thinking imagination will improve performance. That's the theory that we're testing. And the same for this normal here. It's all on the positive side. So this is a theory saying we're going to get a 5% positive difference between conditions. Okay? Maybe a 5% improvement, for example. Now I sort of have a default rule. I have this curve come down. A normal never quite comes down to 0, right? But it comes down pretty close to 0 at a certain point. If this is a theory with a directional prediction, we want the plausibility to come down to close to 0 here. What that means is that because the normal's symmetric, it's going to come down to close to 0 around about 10%. So what this theory amounts to is saying, I don't know what the effect is. I think 5% is pretty likely, and it's going to be somewhere between 0 and 10%. Okay. Now, incidentally, none of these distributions I'm talking about are distributions of your data. So this is a distribution you've never, unless you've done Bayesian statistics, you've never seen or thought about before, because it's the plausibility of different population values. So even when I had the uniform, I wasn't saying that my data are distributed like a rectangle. In fact, my calculator assumes normal distributions, just like standard parametric tests. It's saying when you think about what my theory predicts, how plausible are different population mean differences. Okay. Now, in fact, that isn't quite the distribution I use in that situation. I use a half normal, which is a normal which did have a mean of 0, and I've chopped off half of it. And I set the standard deviation of that distribution to the expected value, say 5% in this case. Now, there's several things are going to strike you as strange about that. Don't worry if you think this is all strange. I'll just explain why. So now what this distribution is saying is smaller values are more likely than bigger values. Okay. And again, if I set the standard deviation to 5, it's giving me a range of 0 to roughly 10%. Okay. So the standard deviation here I set to the roughly expected value that I think I'm going to get, say from a meta-analysis, a prior study, something like that. Now this might look slightly strange because I'm saying the most plausible values are the ones really close to the null hypothesis. Now the reason why that's useful, and Bayesian statisticians often do things like this, they use distributions which peak at the null. That's because the precise shape of these distributions, normally you don't have strong intuitions what they should be. Your intuition is saying, well, I think the population effect is somewhere around 5%, but of course it could be less than that, could be more than that, probably not more than 10%. That might be the extent of your scientific intuitions. Right. Now the exact shape of this distribution, other than that, is irrelevant to you. Now what happens when you peak this around 0, it makes fairly similar predictions in many situations as the null hypothesis itself, because they're both saying these values are the most likely. That makes it harder to distinguish the theories. So that means when you do get diagnostic evidence, you've done so despite your assumptions, despite the assumptions that you don't care about, you see. So I hope that makes some sense. We just rig things slightly against us so that when we do get good support for one theory or the other, it's been despite what we've done. So we haven't cherry-picked our assumptions. Because where Bayes is criticized, and the criticism is fair in the sense that you have to think about this, is we're picking some distribution here, and there's some arbitrariness in the choice of that distribution, and that our scientific judgments don't completely specify that distribution. So what's the solution? Well, one solution is you rig it so that things go against finding compelling evidence either way. Then when you do get compelling evidence, you can trust it. So that now is the difficult bit over. Okay. So as I carry on now, hopefully what I say makes just sort of normal sense according to your classically trained intuitions. And I'll be illustrating all of this with some examples. So don't worry, we'll come back to those difficult bits. Because it's really very easy. But it's not easy the first time you do it, or the second time, or the third time. But you'll get to a point where in 60 seconds you could do a Bayesian analysis of some effect of interest. Now, to know how strongly the data support one theory rather than another, you need to know not just what the theories predict, but you need to know what the data are, right? And a sufficient summary of the data in a t-test situation is the mean difference that you got and the standard error of that mean. Now, that's exactly the same as you would use in a t-test, because in fact the t-test just is the mean difference divided by its standard error. So that's useful in terms of using my online calculator, because what you need to enter into the calculator is the mean difference and its standard error. Now, the mean difference you can get easily enough from whatever software you use. You just look at the difference in condition 1, the mean in condition 1, the mean in condition 2, and you take the difference. So you can get that. But now you need to know the right standard error of difference for that mean. How do you find that? Well, get your SPSS, Excel, or whatever you use to do a t-test. And then if you divide your mean difference by the t, you get exactly the right standard error for that situation. It doesn't matter if it's a between subjects or within subjects, a one sample, a mixed design. It doesn't matter. Wherever you get a t-test and something you're doing a t-test on, if you divide that mean difference or the regression coefficient, doesn't matter what it is, anything, by the t, you'll get the right standard error. Okay. And I just, at the very bottom there, put a note, which I use this all the time when I do Bayes factors on papers. If you take an f with 1 degree of freedom, that is a t-value. Well, it's a t-value squared. And it doesn't matter what the f is. It could be a three-way interaction. If it's got 1 degree of freedom there, it's essentially a t-test. You can square root that f to get a t, and you can do a Bayes factor using my software. So to calculate a Bayes factor, Google my name. I think it's the first one that comes up. But anyway, you find my homepage as a picture of me with my hand on a yak at 5,000 meters. Then that's the right site. And then just below the yak, it says, click here for Bayes factor calculator. You click on that, and there you have it. And incidentally, there's some other software come out, JASP. That does things slightly differently, but that's going to be very useful software for Bayes. And in a few months, they'll have my precise way of doing Bayes factors built into that as well. So this is what then pops up. It asks you here, what is the sample mean? That means, well, if it was a one sample case, it's the sample mean. Or the mean difference, or whatever it is you're doing your t-test on. So let's say mean difference, that's where you put into there. Top box standard error. I probably should have put that the other way around. People tend to put the mean first and the standard error in. Just remember it's the second box is the mean, and then the top box is the standard error. Now what this is asking is the distribution of the plausibility of different population values given the theory uniform? So it's asking if you wanted to use a uniform or something else. Okay. Now, if you click yes for uniform, you're saying it's a uniform. Two more boxes come up. One asks you for the lower bound of the uniform. By default, I put in 0. But you might be able to think in that situation, no, there's some minimal interesting effect size. And if you can really specify that, you can put it in. Normally, when you think of a realistic minimal value, the smallest value you could possibly be interested in, it doesn't make any difference if you put in 0. Okay, so I just have 0 as a default. And then the upper bound, well, that's the maximum that you thought of, like in the sports move example. It's how well people would really do with actually doing the movement. And then that's it. So you see you typed in 4 numbers, mean, standard error, a lower bound and an upper bound, and you click go, and then it tells you your Bayes factor. That's what I mean, it's quite easy. Now you might have said it's not a uniform, it's a normal. That means it's a normal of some sort. Now if you're doing I've called one-tailed or two-tailed, If you have doubts or funny feelings that something's wrong about one-tailed t-tests, don't worry about that. When it comes to Bayes, it's completely different. And whatever thoughts you have about one-tailed t-tests being somehow cheating or bad or something like that, that doesn't apply to Bayes. Okay. What it means by one-tailed or two-tailed here is just, are you doing the full normal, or are you doing that funny chopped-off normal that I mentioned? So for the one-tailed, you put a 1 there and a 0 for the mean. And then for this box, which is the standard deviation, you put in the expected value, the rough sort of value that the scale of effect you think you would get. So if a meta-analysis says it's, or the previous experiment or the other condition in your experiment says the difference in N400 is 10 microvolts for women, and you want to test the men, you could put a 10 in there. That's roughly the sort of thing you expect. Okay, so that's the rough expected value you put in there. Okay. If your predictions, you wanted to make them, they could go in either way. The people could be good in one condition or worse in that condition compared to the other. Then say it's two-tailed. And you could still put a 0 here for the reasons I spoke about before to make it hard to distinguish the null hypothesis from the alternative. And then you put your expected effect in there. And then that's it. You click go and you get a Bayes factor. So now we return to the dance of the p-values of Jeff Cumming. And I've just written out these p-values here. And you see they dance, they jump all over the place. 0.006, you're ecstatic. Next experiment, 0.476. You're going to give up your PhD, you burn it. Now, let's look at the Bayes factor. So what I've done in each case is calculated Bayes factor. And what I've assumed, by the way, the true population effect here is 10. I just assumed we had some pretty good information that just told us if there is an effect, it could be on the order of magnitude of 10. So I've done a half normal with a standard deviation of 10. So this relates to a point I said before about if you get a significant effect and it's roughly what you expect, Fisherian p-values and Bayes factors will tend to agree, just as Jeffrey said. But that only applies when your expectations are reasonably well informed. So what I've done is I've put 10 as our expectation for a half normal, and I've calculated Bayes factors here. So now in the first case, we have a p-value of 0.23, non-significant. The corresponding Bayes factor is 1.73. Don't know if you remember what 1.73 means. So it means it's above 1. So actually that's support for H1. You've got more evidence for H1 than H0. Okay. This non-significant effect is not evidence for the null hypothesis at all. If you got this non-significant p equals 0.23, you should not have less confidence in there being an effect there. In fact, if anything, you should have a bit more confidence. You shouldn't think, oh my God, this imagination stuff, this doesn't work. What was I thinking of? Can I start a new PhD now? You shouldn't be thinking that. You think, oh, actually it's insensitive. But if anything, it's telling me I should be more confident in there being an effect. Right. Now, one thing you notice, where there is a significant result, like here, 0.024, in every case, the Bayes factor is around about 3 or more. So there's the correspondence I talked about. So then what does Bayes give you? Well, it tells you how to interpret the non-significant results here. And in fact, as it happens in every single case of a non-significant result, even this 0.817, which is, as it were, you might say, very non-significant, the Bayes factor is 0.46. So now what does 0.46 mean? That is some evidence for H0, but it's above a third. It was above our conventional cutoff. So you'd treat this as insensitive. Right? You'd say we need more data. Now, as it happened, in every single case here, the non-significant result corresponded to insensitive evidence, which happens to be, in this case, it happens to mean you would not draw a wrong conclusion. You would either say substantial evidence for the alternative, substantial evidence for the alternative, or insensitive. That's not to say Bayes factors will always give you the right conclusion. They won't, because statistics must always mislead sometimes. Otherwise, there's no point doing statistics. You collect one observation and you just go with that. So Bayes factors will sometimes mislead. But what I want you to get from this is the sense in which they mislead less often than how people normally use p-values. Because how people normally use p-values is to say it's non-significant, therefore there's no difference. But in this case, the data were utterly non-discriminating and shouldn't have moved your confidence one iota one way or the other. So I call that the Tai Chi of the Bayes factors to illustrate it's far more graceful than p-values. Now, it's so tempting to go from a non-significant result to saying subjects were non-significantly above chance to say subjects were at chance. To say that subjects were non-significantly above chance is just a statement of the results you happen to get. To say subjects were at chance on this test could be interpreted as a statement about the population, and that would be wrong to say that. So whenever you get a non-significant result, don't say there was no effect. That's potentially misleading. Just say there was not a significant effect. And then that's just a statement of fact. Now, I went through the March issue of Journal of Experimental Psychology General, and I looked at every paper. There was one paper that used Bayes, so I'm going to exclude that. But in all other cases, every single paper went from a non-significant result to asserting no difference in order to draw theoretical conclusions. On no other grounds than it was non-significant, which is completely illegitimate. But I sort of knew I was going to find that because I know every talk I go to, every paper I read, someone draws the conclusion of no difference from a non-significant result. So the problem is completely widespread, and I think extremely harmful to theory development if in almost every paper and every talk you go to, an illegitimate conclusion is drawn which has no statistical basis to it. Where it often comes up is in an interaction. You get a significant interaction, or you say you might get a significant effect, but it doesn't interact with gender. So you say, men and women, the effect applied equally to men and women. Well, no, you don't know that. You've got a non-significant interaction. You don't know that men and women were the same. It might be you just didn't have diagnostic evidence. You just didn't have evidence one way or the other. Or you get a significant interaction, so you do simple effects, and you say, for men, there was an effect of taking ginseng, but for women, there's no effect. Well, you don't know there was no effect for women. The interaction just tells you it was bigger for men than women, but maybe there's still a residual effect for women. You don't know that just from the non-significant result. But as I say, in every single paper in a prestige journal, JP General, these sorts of incorrect conclusions were drawn. But the solution is easy. You type in 4 numbers on my online calculator, and you know. So let's apply this in implicit learning context. Let's say you take native English speakers, and they do something Rebishatian or Williamsian, and they have a Polish grammar with English words, and they rate it for meaningfulness. And then you say, oh, by the way, we had a funny sort of grammar there. Here's some new sentences because you judge them as grammatical or not. And you then you get them for each judgment to say, did you base this just literally on a guess? It was completely random, the basis of your judgment. Or you had some feeling like intuition or familiarity that guided you. Or you had some rule that you could state fast, or you recollected this sentence having occurred before. And then you find the percent correct on each of them, and you find that they're all significant except for guess, and indeed they're 50% correct on guess, 50% being chance. The temptation would be to say they're at chance on guessing. So they don't know, they don't have any knowledge, any genuine knowledge of grammaticality when they say they're guessing. So there's no unconscious knowledge of the sort that expresses itself when you say you're guessing, when you don't know that you know at all. So do people have no knowledge when they say they're guessing? Well, based on what I've said so far, I hope you would say, I don't know yet. All you've told me is it's non-significant. For all I know, you just have insensitivity. And incidentally, I chose this example because I want to illustrate something. People often say, but they're exactly at chance, they're exactly at 50%. Or the sample mean difference was exactly 0, so that's good evidence for there being no difference, right? Because my sample difference was 0. Well, that just depends on your standard error. If you have a big enough standard error, you very easily, the population difference could be 55%, you could very easily have a sample difference of 50%. Why not? It just depends on how big your standard error is. So what can we do here? Well, now it comes to a matter of, some Bayesians like to have sort of default rules. I don't like that. What I like is you specify what you expect based on your scientific judgment. And so with using these structural knowledge attributions, I happen to know, at least with the sorts of materials that I use, that guess responses are almost always less than intuition and the other responses, right? So intuition defines a reasonable maximum I could expect with guessing knowledge. So I could use a uniform that goes from, I put 10 there, and it goes from 0 to 10, and the reason is my base factor calculator always assumes that the null hypothesis is 0. So in this case, what you do is you subtract 50 from your numbers. So you just rescale it so that 0 becomes the chance baseline value. So 60% becomes 10, because it's 10% above baseline, right? So I put a uniform from 0 to 10. I put in for my mean, I'd put in 0, okay, because there's 0 difference from baseline. And I'd put in a standard error of 5. And if you do that, you get a base factor, in this case, of 0.6. So what does that tell you? It's insensitive, right? Okay, because it's not less than a third. So for all I know, there is good knowledge when people say they're guessing. I haven't ruled out that sort of knowledge. Data insensitive. Now often what I do is I combine guessing and intuition together as cases where you have unconscious structural knowledge, compare with rules and memory as cases where you have conscious structural knowledge. Let's say previous experiment using similar materials found that when people guess or use intuition, the classification is 59% correct. But you obtain 51% non-significant. So in this case, I'd use a half normal because I have, this is a situation where I can use a past case to say, well, this was a very similar situation. I think it's relevantly similar. Maybe it was German grammar rather than Polish grammar, and but I've got no reason to think that makes a difference. And so they got 9% above baseline, so I use a half normal of 9%. Okay, so I'm just plugging in an expected value. Now here the base factor with those numbers is 0.31. That is actually good evidence for the null hypothesis. And the reason for that is this standard error is actually quite small. You see, 1% standard error. Because they're tight standard error. If I'd increased that to 5%, that would have been insensitive. So obviously the sensitivity of your experiment depends on how small you can get your error down, which depends on things like numbers of subjects and numbers of trials. So I had another example, but I'll just skip over that. And so my general rules are these. If you can determine an approximate size of a effect that you think is roughly expected, I'd either use a half normal if my theory makes a directional prediction, or a full normal if the theory allows effects to go in both directions, and set the standard deviation to the expected effect. So that's one rule of thumb. The other rule of thumb is, if I can think of an approximate maximum value, I do a uniform from 0 to that maximum. The maximum probably might not strike you as so intuitive, in the sense we're not used to thinking that way, but I actually found about half the time I use the uniform, because I can think of a maximum, and half the time I can think of a way of getting a roughly expected value in that situation. So I use those about equally. The material I've been through in this talk is in this Frontiers paper, and it has lots of examples in there. And once you've been through enough examples, I think you'll be able to see how to apply it in your case. But if you have any questions, feel free to email me, because I'll be able to make probably a pretty quick judgment as to what I'll do in that situation. If you go to my website, I've also put up a number of papers where I've done this. So I've probably published a couple of dozen papers now with this in. And you can see how I've phrased it so that people understand what I'm doing and just how I set it up. And incidentally, I've never had any trouble with reviewers on this. In fact, quite the opposite. They've often said, could you take that Bayesian analysis out of the footnotes, put it in the main text? Or could you mention it in the abstract that you've done this? They've always said that they like the Bayes. Right, so don't worry about that. As long as you present it in the right way and just look at my papers for examples, it goes down well. In fact, my strategy has been to do the orthodox analyses and then put Bayes alongside that. And I think that's what we should be doing while we're learning to sort of calibrate our intuitions, understand what we're doing, have a debate about the best way of doing these things. So I was quite surprised when the Association for Psychological Science, the APS, which runs some of the high prestige journals like Psychological Science, they said no editor for any of their journals can refuse a paper for being purely Bayesian. So that was even a bigger step than I'd probably take. As far as they're concerned, if all the results were Bayesian and no p-values, they'll be happy. So things are changing very rapidly now, and I see Bayes in more and more papers outside of my own. I'll stop there and take questions.